And I'll please ask Rodrigo Carvajal to please speak up and share your screen. Are you around?
Yeah, can you hear me?
Okay. So can you please share your screen? Very good. So you're going to present your work on using a series of machine learning models for the detection of high-redshift radio galaxy candidates. You have 12 minutes, and I'll warn you on Slack 3 minutes before and 1 minute before. Go ahead. Thank you.
Okay. Good morning. I'm Rodrigo, a PhD student from the Institute of Astrophysics and Space Sciences at the University of Lisbon. And let me first thank the organizers for giving me the opportunity to talk about this work that we carried out with the extragalactic group in our institute. And just as an introduction, yes, let me talk to you about Radio Galaxies. So these are AGNs that are very active or very bright in the radio. So the idea is that we can detect their emission on the actual AGN, actual center of the galaxy, and also some jets, as you can see in the image in the right. So they are strong enough to be detected in the radio. That's like a very simplistic definition of them. And we are focused on studying them because we can detect at very high redshift, and we can use them to study the end of the epoch of reionization and also the overall AGN evolution. So let's go and study them, but we want to detect as much of them as we can, and we have several catalogs and observation surveys, and we have some problems. So first, since we want to go for high redshift, observations of these objects take very long time, and we have some issues of pinpointing the actual emission of the detection, which can be in the optical or infrared, to the radio, and future and actual and present surveys can deliver a huge amount of data, as you can see in the table in the left. So typical and traditional AGN detection methods and redshift determination techniques will be very hard to use in the future. So what can we do to solve one of these problems? And of course, we can call the star of the show, which is machine learning. And in our case, we're going to do something at a lower level, and we are going to use what was called here in the conference as a shallow learning. And we want to create a series of different models to predict separately the presence of AGN, then if this AGN will have a radio emission, and after that, the redshift of this object. And why using a series of models and not only one with all of these quantities? Because we want to have more control over the features that we are going to use, and that in looking for the goal of trying to interpret the model, trying to extract as much information, physical or correlation information, let's say, from the modeling itself. So let's go for the data that we use for that. And we started with the head spring field, which is in the northern sky. And in this area that we see here, which is the actual coverage in the radio from the LOTS survey and in its first data release, we took every object that was detected in the near infrared from the CatWise catalog. So we have almost 7 million objects, galaxies, stars, AGNs, everything. And then we obtained the counterparts from several catalogs in the radio, infrared, visible, ultraviolet, and X-ray. So with that huge catalog, so we are talking about only tabular data, then we went to the million quasar catalog again and cross-matched that and obtained all the objects that are classified as an AGN by any means, not only SDSS or some kind of specific method of detecting them. So here we have some early distributions of this data. So in the upper panel, we have that distribution of all the objects, all the 7 million. And in colors with very horrible contours, we have the distribution of the radio, non-radio AGNs, the original data. And in the bottom panel, we have the same, but for the redshifts, the original redshifts, spectroscopic redshifts. Then for the data, we created, of course, some colors and magnitudes, and ratios of magnitudes, and some flags of being an AGN, having radio emission and X-ray emission. And finally, we identified around 30,000 objects as being AGNs by this catalog. So that's a very, very low fraction of the full data. So our sample is very unbalanced, as you can see. For the data, for the model, sorry, as I told you, we are going for a shallow learning. So that's using typical models like random forests, KNN, and things like that. And we're separated with train and validation, and we applied a model stacking. So we are taking the information from several models into one meta learner that will hopefully help us get better information from all the areas of the parameter space. We did some feature selection, and we tried to fix for unbalancing the radio model for the radio model. And the metrics are going to be the difference in the redshift and the Matthews correlation coefficient being a good metric for unbalanced data. So let's go for the actual results. So after training the data in this headdex area, we apply the combination of them. So one step after the other in a different area of the sky, just to validate it in a cleaner way, let's say. So we went for the stripe 82 area. So it's, of course, in another part of the sky, but we took almost the same data. So we have the same WISE data, radio, X-ray, ultraviolet. And in this case, we start with almost 400,000 objects of all kinds in this area, and almost 3,000 of them have been labeled as AGNs. And we apply the models in series. So first the AGN prediction, then for the ones that are predicted as AGNs, we apply the model of radio prediction. And for those that are both AGN and radio objects, we calculated the redshift. And we have here, just for you to see it, the confusion matrices of the application, this serial application of the models. And in the right side, you have the prediction of the redshift with the dispersion in this normalized redshift value. So after applying these models, the good thing is that out of the almost 4 million objects in the stripe 82 area, we have 266 radio AGN candidates with redshift prediction. And I have a snapshot of the table. So it's just to see that we can derive sort of a catalog of it. And we have the prediction and the comparison. And let's see one example of them. So this is our prediction with the highest redshift. And we can see that it's been, we have the original data, pan-stars, and WISE. And importantly, we predicted it to have radio emission. And if we go to a deep observation of that area, VLA, we can see that there's actually radio emission. So we are predicting, okay, our data, our objects. But after the actual prediction and having a good catalog, we want to see if we can do something else with the models. So first, we can go for feature importances. And we see, of course, that we have a list of features that can help us understanding what's going on with each of the models, but we want to do better than this. So we went for a different approach, and we extracted the Shapley values, which can do something in the line of feature importance, but for each individual prediction. I mean, for each AGN, we can see which feature impacts the most or the least for the actual final value of the probability of being an AGN or the actual redshift prediction. So I have an example of this, a very simplistic one. So in the x-axis, we have a flag that I created being having X-ray emission. So I'm sorry, this should be the opposite, but having a 0 means that there is an AGN emission, and having 1, it means that it doesn't have an X-ray emission. And then the y-axis is the Shapley value. So that means the impact in the prediction of the AGN detection. So we have that if we have we have X-ray emission, that means that the object predicted, will have a high probability of being an AGN. So that we of course know that in reality, having X-ray, it's a very good tracer of being an AGN, but we can detect it only from the model, which doesn't know anything about the physics relying below of this. So as final thoughts, we can see that we can work with not super clean data to have interesting results. And we can do some kind of transferability in areas of the sky with minor changes in data set. And using the models separately can help us understanding each of the steps and understanding sort of the correlations and physics behind each of the modeling. And that's the same. So we can try to probably get new discoveries on physics. And for future steps, we want to include uncertainties, of course, and try to add some new features like morphological or some combinations of magnitudes or things like that. And something very difficult, try to tackle imbalance of the data. That's super hard, but we are working on that for the moment. And I will stop here, and thank you very much for your attention. I will take any questions from you.
Thank you. So, do we have any question in the audience? While people thinking a bit, can you go back to the last part of your talk when you were discussing, trying to link back to which are the more relevant features and more relevant parameters? So you presented one of them. You were alluding to, in your conclusion, to possible correlation. Can you elaborate a bit more here? Are there other parameters that you've looked into?
This slide, you mean?
Yeah.
Yeah. So this is a very simple example, like an obvious result that having X-ray will imply more certainly that we will have an AGN. Mm-hmm. So that it's for showing that the model is actually telling us that for the sources that have an X-ray detection, the model will lean its prediction to telling me that it's going to be an AGN actually. So that's the point of it. And I didn't mention this, but the colors are, in this case, just a astronomical color. Mm-hmm. So this is from pan-stars. And again, if we have redder objects, the probability of being an AGN will be increased again. So that's the point of trying to use this tool, is trying to get the interactions between the features for each individual object, as is not really possible with feature importance, because you only have a list that the ones that help you discriminate better between one subsample of the data or things like that. But here it's already possible to say something more. That's the point of it.
Okay, so that this is the only example you have right now. I mean, this one is as you said, rather obvious one. But that you've not gone much further than that for now, right?
Let me. I have one more here. Yeah, for the moment, it's not. I'm not obtaining like a super strange physics because, as it was also discussed here, if we find something strange, we don't believe it. So maybe we can work again. There's something wrong, and we are probably in that step. But for the moment, yeah, let's say we are obtaining like sort of obvious results that being a radar object will be more probable to have an AGN and things like that. But yeah.
Okay. Any other question in the room or on Slack? No. So if not, first I want to apologize for the static during your talk. We are investigating the issue. I'm really sorry about that. And I want all of us to please thank all of the speakers of this morning session again.